Yes.
Okay, nice. Then welcome to another meeting of the North Pole Reliability Initiative. Yeah, given that there are many new faces and not so many pointy ears as usual, I will think to start with some onboarding material for you, if this works. Yeah, so many of you, if you are subscribed to the North Pole mailing list, you will remember the incidents that we had on the Northwest toy assembly facility and this tragic Christmas evening of 2023. Well, the gift delivery system was malfunctioning. So after careful investigation of these problems, we came out to a conclusion that there were some glitches in the hardware. The Sleigh was really in bad shape, and that brought us to bringing up this initiative to improve the reliability of all of our facilities and instruments. So the idea of this is to take care of the monitoring of all the hardware that we deploy in the assembly lines, in the embedded devices on the Sleigh, and other wearables that might be around on the elves. And you might be wondering, okay, why do we actually need to monitor hardware? It's just hardware. Well, if we look at the typical failure rate on different components and hardware, we would see different behaviors. So we can start by saying the early failures, which account for devices that have some manufacturing problems. Those, as soon as they're deployed, they tend to fail early, let's say, and that kind of failure just fades away over time. Then we would have some custom random failures that appear randomly and depend on the component reliability. And finally, we would have the wear out failures, which actually start creeping up at the end of the lifetime. That means that the components are being used, and the failures due to usage start to appear. Of course, when we observe a large population of components, we don't see these failures by their own, but we actually observe what is called this bathtub curve due to the shape. And with monitoring hardware or other components, what we aim to is to detect this wear out phase. So we want to see when this curve starts to grow. So we aim to detect this increase after the useful life period of the devices. So yeah, I mean, like I said, this is the bathtub curve, but for some reason in the North Pole they actually have a different name for it. We're going to focus mostly on silicon devices today, and mainly into the degradation mechanisms, which are the bias temperature instability and the hot current injection. There are some references if you want to check the details on those. We're not going to go into detail, but we care about the effects of these mechanisms, and that is mainly that BTI and HCI increase threshold voltage of transistors. That means the voltage that is needed to activate the devices. And also, as it happens on all digital devices, they become slower, and that brings risk of increasing, brings the risk of increasing timing issues, like we saw on the gift delivery system. So, with this in mind, we are gonna focus the talk of today in mainly the communication, navigation, and gift subsystem of the Sleigh. That means that we're going to look at the FPGAs and the microcontrollers that are dealing with those systems. So the big questions here is, how do we actually detect and monitor the aging on these devices without changing them, right? I mean, these are components off the shelf, and we just buy them, we don't modify them. That's cheaper, you know, we just order in DigiKey and build the Sleigh once every 100 years, so that's, you know, it's much easier. So the three parts of the talk are going to be focused on how do we detect aging on static RAMs and microcontrollers. Then we're going to move to the FPGAs and see how the propagation delay changes over time. And finally, we're going to see how we can detect aging on microcontrollers, not on the SRAM, but directly on the core and the execution part. So we start with the SRAM. For ones who are not familiar with it, static RAM cell with 6 transistors looks like this. This is basically holding 1 bit of information. It's made of 6 transistors, so 2-axis transistor, 2-axis. The value here in Q, the voltage here gives us whether the cell holds a 1 or a 0, and these 2 cross-couple inverters. But if we look more in detail, it actually looks like this, where the inverters are made out of 4 more transistors in this cross-coupled fashion with these 2 inverter transistors on the top. So why do we care about this? Well, as cell ages, the threshold voltage of the transistors change. That can bring different problems. For instance, if we have radiation, increased threshold voltage makes some cells more susceptible to bit flips. That can happen, for instance, if we are flying at high altitude in the North Pole and then we are hitting more radiation, then the bit flips are much more complicated, right? So we're going to see whether we can actually see the threshold voltage change on the SRAMs from the software perspective, right? Just without changing any hardware. So the working principle that we can apply is looking at the cell startup. So when we never power up the cells, we're going to increase the VDD voltage linearly because, well, the power supply doesn't really give a step in voltage, but rather a ramp. Let's imagine here we have the ramp of voltage that is applied to the transistors. We're going to focus on M2 and M4 and see what happens when we turn on the cell. In the beginning, we look first at M4. We see that the voltage at the output, so at Q, starts to go linearly with the power supply voltage and also the gate source voltage that is trying to activate the transistor starts to grow linearly. The same happens to M2 in the same fashion. In this stage, both transistors are starting, they're still in cutoff, so not conducting, and both are trying to win the race of who activates first. But now, let's imagine that for some reason, let's say aging, the threshold voltage of M2 is a bit higher. So it increased due to usage. That means that the threshold voltage of M4 is a bit lower. Given that, this part that is going down will hit the threshold voltage of M4 first. That means that at some point, M4 will turn on and start conducting more current in this part, reducing the voltage that is sent to the gate of M2. Thus, M2 will not be activated, M4 will go into saturation, and whenever the VDD voltage here at the source of M4 starts going even higher due to the VDD increase, M4 will go into the linear mode, and M2 will just remain cut off with 0 voltage on the 0 volts on the gate source. That means that effectively the output of the cell here in Q is a 1 or VDD, and M4 won the race. That's because the threshold voltage of M4 was lower than the one from M2. So how can we use this? Well, in general, we see that there is a small difference between transistors and the values will be random, so this race will be randomly jittering due to temperature and external influences. But when we have a big difference between the threshold voltage, the value will be kind of biased and stable. So how does this get stabilized? Well, with usage and stress through the aging mechanisms that we saw, for instance, BTI will increase the threshold voltage of the transistors that are active, and that will bias the cells towards always turning on in a certain value. So what's the thesis here that we want to see? Where in the beginning, we would expect a new SRAM to have around 50% of ones and 50% of zeros, and then as soon as it ages, it will be biased over, so it will drift from this and will be biased towards some value. This is the idea. So, how can we use this startup to extract features and detect the device usage? Well, that's what we're going to look at. We evaluated multiple devices, 154 ST microelectronics microcontrollers from some public testbeds, the IoT Lab testbed, and also some microcontrollers from the European XFL at DSE. We took all the microcontrollers and basically turned them on 1,000 times, each of them, and looked at the SRAM values at startup. This is the distribution of usage of the different devices that we looked at. And we basically looked at all of the bits and calculate different features from this. So if we start calculating the amount of ones that we have, depending on the usage time of the devices, we can see there's a slight trend here towards having more percentage of ones, so more ones in the SRAM as devices age. Here on top we can see the correlation between the two variables. So we observe this also in other values of percent of one, not only in the mean, but also the maximum and the minimum. And from this we conclude that the percentage of 1 increases as we expected with the device usage. So now let's imagine that this is all of the bits of the memory. Each of the squares is 1 bit, and we can imagine this as a tiny present where we open and we don't know where it's there. Maybe it's a toy, maybe there's code, maybe something that's going to bite us. I hope not. And then we actually take this and run the startup multiple times, so n samples of the same microcontroller. For each of the bits we can calculate the probability of 1, so that means basically the average value of each of the bits over that. And we can kind of classify bits in stable bits. That means that bits are always or almost always hold 1, and bits are almost always hold 0. And then some unstable bits that switch much more are closer to 0.5, 0.6. To see this more clearly, we propose to use bit activity, which is basically the minimum value between the probability of 1 and 1 minus the probability of 1. And if we actually take all of the bits and encode it in bit activity and see this kind of square plot for a real device, it looks more like this. So this is the bit activity of an Atmel device from the European XFL that we measured. And we can see that at some point here, there's something going on, like 200 or so, but it's not so clear. But because the order doesn't really matter in the horizontal, we can actually order it by bit activity, and then boom, we see a spike here, which actually correlates to the firmware RAM usage that these devices have been running over multiple years before we run the test. That means that we can actually see the footprint of the firmware, because this part of bit activity, these cells here are much more random because they're not biased due to the constant stress that these other bits have been following. When we did this with the other devices from the test bed, boom, it doesn't seem to be so obvious. One reason could be that the previous microcontrollers were always running the same firmware, and these ones come actually from a public test bed which run any firmware that a Riot developer probably was flashing on that. So, okay, we need to add some more features to this. We can calculate for each of the devices the correlation between the probability of 1 and the memory block. So if we block the memory in 1K bytes and calculate the probability of 1 for that block, then we can do a linear regression and use the features from this line to actually deduce some interesting information from the devices. So if we look, for instance, at the intercept of the linear regression, or we look at the correlation between the probability of 1 and the address, we can see that in this case, the intercept tends to be higher as the usage passes. That means that this line gets steeper towards down, and also that this correlation actually gets higher as devices are used. So from this we can actually conclude that the bits in the lower part of the memory, from the startup point, we see them in 1. As we saw previously, when the SRAM memory starts in 1, that means that during usage they actually were holding a 0, which, if you think about it, kind of makes sense, because normally the lower part of the memory is the one that you're using, the one that you're initializing to your variables, and then tend to hold 0 because you initialize into that. And secondly, we see that there's an increased correlation between the probability of 1 and the address with the usage. That means that, well, the devices are actually aging. And then finally, another feature that we extracted from this was calculating a one-dimensional Fourier transform with the position of the bits on the memory. And it was something interesting. Here in the top, we can see the spectrum of a younger device, so 1.2 months, versus a device that's almost 18 months running. And although both have some activity on the higher part, which is basically the noise, we can see that there's a much more increase here in the lower frequencies, or in the lower part of the spectrum, which actually suggests that there are some patterns in the device usage. Although the firmware was not the same, there is some kind of like pattern on how the bits of the memory in that part start up. So with all this, we went and do some machine learning model training, and we tried to classify the usage of the devices with different models using all these features and others that we included. the first classification, basically we changed how big the boxes of the classification are from 1 month resolution to having 9 months. That means that at this point here is basically two classification problem, and we can see that the F1 score at this point in 8-9 months, it's relatively good, particularly in the k-near neighbors. So we can estimate with 0.65 F1 at 6 months resolution and a bit more at 9 month resolution the usage of the devices based on the features that we presented. If you need more details, then there is reference 2 that you can go to see more about the machine learning part of this work. So, in summary, we actually deduce that the share of ones increase with the use time. The lower part of the memory tends to hold 0, and we only observe this by looking at the RAM multiple times. And we also found that using the spatial frequencies helped us understand the type of usage on the memory cells. And then using the features that we extracted, we could estimate the time, the usage time of the SRAM just based on the startup patterns. So now we move on to FPGAs. That's the other type of devices. In this case, we care about the propagation delay. That means how the device actually gets slower over time and the signals propagate slower, possibly causing timing errors. So for this, what we basically deployed was multiple of these ring oscillator sensors, which are composed of an odd number of inverters that will basically make an oscillating frequency here at the end. And the frequency of that oscillation will depend on the size of the oscillator and the propagation time that is actually what we want to measure of all these circuits. So in the end, we basically need to measure the frequency of the number of oscillations, and then we can get a proportion of the time that it takes the signal to propagate through all of this chain of inverters. So that's what we want to use as a sensing mechanism. And the concept is that we have multiple of the devices. We run this self-test, so that means that the devices just actually measure themselves. We collect the data, we do some statistical analysis and run some machine learning models to detect outlier degradations and also to be able to forecast how is this propagation delay going to be in the future. This is really important because if we know how this will be in the future, then we can also do some predictive maintenance and replace the devices before they crash the toy assembly. So, how do we actually measure the degradation and detect the areas that are more aged on the devices, and how do we forecast this degradation based on historical data? So, the first what I'm going to present is how we measure this. In the facility, we have shutdown periods which are 6 months apart, and then we have the continuous operation. In the first shutdown, we made a high resolution measurement, basically, where we have the device for ourselves and we just deploy multiple of these sensors. And then during operation, we have a lower resolution where we deploy less sensors, but we measure every 2 hours. So we have two types of measurements. One is the comparison between the two shutdowns, and another one is the continuous monitoring of this. So we're going to start with the shutdown period. Actually, well, the measurements were taken on the European XFL, which is the linear superconductor accelerator that is running here in Daisy. It actually goes from Warrenfeld to Schönefeld, 3.4 kilometers long. There is where we actually measured more than 200 devices to come up with these measurements. So, shutdown measurements. If we imagine that this is the FPGA, which is made out of multiple logic blocks, and we deploy all of the ring oscillators on different parts of the FPGA, but knowing where we are actually locating the ring oscillators, we can compare the frequency between the two shutdowns and have an estimation of how much the ring oscillator or that area has been degraded. So if between each oscillator we consider a linear interpolation, given that most of the wear out comes from temperature and is similar in the area of the ring oscillator, we can come up with a plot like follows. So here we have the median frequency shift, so how much the ring oscillators change across all of the devices. More red areas here have a negative shift. That means that the ring oscillators are slower after the 6 months, and more blue parts are a bit not so bad. So it doesn't shift so much, like 0% in some areas, or even slightly negative, which can be some healing mechanisms, but we are not going to look into that. But today what's important is actually to see that these certain areas present denser degradation, like here in the lower left corner, or in this part here around 80 and 100 of the y coordinates. What's interesting is that because we know what's running actually in that part during the operation, we can actually pinpoint what's happening. So in this area, I mean, these boards that we measured, there's actually ADC samples from superconducting cavities, and they're actually doing ADC samples constantly. That's the only thing they do. So they have to process this data as fast as possible, and that part is running here. That means high speed, high switching frequency, and high temperature, which actually ages that part. And another part that is interesting, what's going on here, is the DDR3 RAM logic, which, because basically the RAM is connected in pins in this area, we want all the IP cores that use it to be in this part, and again, a lot of switching activity and a lot of usage constantly going on here in this area, which seem to have aged this area much more than the rest. So now we move to the continuous monitoring, which is measurements every 2 hours on all the devices. And if we look at the relative frequency shift of the ring oscillators over all this time, we can see that the median is actually negative, so 0.069%. This is the distribution of all of them. And after these 280 days, basically all of them are slower. That's a good finding. So if you were wondering how the data looks like, it's like the blue here. So this is the example of the frequency of a ring oscillator over the 280 days that we observe it. And we can see that clearly the trend goes down, and that happens for all of the ring oscillators. In this case, we were comparing ways to extract the trend from this. So basically extract the noise, which we don't care, and we focus on this lower trend here. You can go to the reference to actually see detailed filter comparison and a time correlation analysis, but we concluded that basically all of the ring oscillators were getting slower. So can we actually use this time series data to predict how this is going to be in the future? Well, the idea is to compare some models to forecast the ring oscillator frequencies based on the time series. We evaluated many of the models also with covariates, basically using environmental measurements such as temperature, voltage, and current of the devices. And when we calculate for the time series that I just showed you, the median average percentage error on multiple models, we come up with this plot. Here in red we can see what's actually what we call the empirical model, traditional empirical model, which is based on just the reliability engineering theory, and we can see that many of the deep learning models that are using covariates, they are much better on the error. But we are going to focus on the theta model here because it's one that is not using really complicated models. It doesn't take so long to train, and it works relatively well compared even to the empirical model. So this is the result for a single time series, but we want to see how this looks like, whether we evaluate multiple of them or we do a backtesting to see how it would have worked when we had deployed this in the past. So we start with the backtesting of the theta model. The backtesting works like this. We have our time series of the ring oscillator, so all of the time that we have the data. Then we split this time into a training length, and a forecast horizon, which is how far into the future we want to look at, and the historical forecast, which is what we are going to compare against. So given this part, the training length, we are going to make a prediction in the rim of the forecast horizon. Then we're going to take this window, move it forward, and then like this, we're going to come with a forecast of which we can actually calculate the error with the actual data, and thus having a backtesting of the model. So for the theta model, we actually tested the backtesting doing different training length and forecast horizon, so how long into the future we can look at, and this is the error for all of these cases. We can see that here the error is kind of similar, except for the one that has the smallest window, which is a bit higher, and they all have this weird structure here, 30 days, and we assume that this might be due to some leftover seasonality on the data, like monthly seasonality, that might be affecting we didn't filter correctly. But basically, all of the training lengths and forecast horizons look pretty well, even for 60 days of future predictions. Now, with this, we can say that, well, the 0.003% of error, even when we have 60 days, when we are using all the previous data. How does it look like when we run this on all of the ring oscillators? Well, the error distributes like this. So it's actually pretty good and pretty much concentrated in this area with a median value of 0.0515% and more than 3/4 of the population between 0.02% of error. So that means that the models are actually doing a good job generalizing all of the ring oscillators. And in summary, we actually observed aging during these 280 days of monitoring. We observed the areas that have more degradation are also correlated to areas of high usage and high frequency switching during operation. And we showed that it's possible to actually predict the propagation delay with machine learning with reasonable errors on a really good 60 days forecast horizon in most of the cases. And to compare to the traditional model, it was actually more than an order of magnitude better than not applying the machine learning. So finally, we're going to move back to the microcontrollers, but not looking into the RAM, but rather the operation. So, like I said before, timing errors is an issue, and that comes due to signals changing when they shouldn't change. So, what's the idea? We have data data signal that is doing a transition at some point in time. The same data signal going through a gate that is, for instance, age would suffer some offset, let's say due to degradation. The switch happens later because it takes longer for the signal to transition, some combinational logic, let's say. But at some point, this signal has to get to a synchronous circuit. That means that we have a clock somewhere. And this clock will give us some sort of hold window and setup window on which the signal shouldn't change. That means that in the hold and the setup, the signal shouldn't change. That's an invalid transition. And considering these 2 points in time, it will give us a window 1 here, in which the signal is allowed to change. So in this case, both signals are changing within the window. That is correct. That's a valid transition. But if we take another frequency that is a bit higher, the window will change. That means that the window is in which we can change is shorter, and the slower signal actually is running some invalid transition if we are running a frequency 2. So, can we use these invalid transitions when we change the frequency to detect whether the signals are degraded? That's the main question. So, we propose to have operational firmware with a software-based self-test like before, where periodically the microcontroller actually injects different test clocks and runs some computational payload to detect what's the maximum frequency at which it can run. The idea is that this maximum error-free frequency, so the maximum frequency at which the signals do the proper transitions, will be degraded as the device is degraded. So we could see by tracking this maximum error-free frequency how fast the microcontroller can run. To do this, we validate the idea with a high temperature experiment where we put the microcontrollers on a high temperature chamber to simulate the degradation, given that this temperature change will affect the propagation delay in the microcontroller. And we also propose to compare multiple payloads. When I say payloads, computing payloads that run and give us this maximum error-free frequency to define which one has a better feature to be deployed potentially in the field and detect the aging via this maximum error-free frequency detection. So the setup looks more like this. We have a little F that is helping here with setting all the microcontrollers in the environmental chamber that will take the microcontrollers from room temperature to 80 degrees. And then we have some control computer that is connected to the chamber, to the ELF, to the USB, clock generator, logic analyzer to measure the time of execution of the payload, and some thermocouple reader to actually measure the temperature on each of the devices. maybe he was too short. It actually was looking like this. It was a bit of a mess. It was too much wires. I think he didn't really see well. But this is what the actual test bed looks like. We compare all of these nuclear devices and different temperatures and different payloads. So when we look at the different payloads that we run to compare, we use the matrix multiplication, where it's basically just computing the determinant of a multiplication of two matrices on the device. Flash read basically reads a region of the flash and calculates a hash based on this. Similarly, the RAM does this, but also writes on the RAM. Then we apply RAM March C test, which typically just tests the bits of the RAM and tries to detect stack up faults or stack at zero and this kind of errors in the RAM writing. This was executed from RAM to reduce the usage of flash compared to the other tests, so we can focus on more on what this happens on the RAM and have a bit of isolation from the flash usage. And similarly happens to the CPU vendor test, which actually tests its registers and ALU flags. It's also run from RAM. Now, in parallel with this, we also have two configurations for the device, which this buffer we call configuration is basically enabling the prefetch buffer, which prefetch the instructions from flash and has some two wait states, so waits two states before doing read operations from the flash, and the unbuffered configuration we call is one that disables the prefetch buffer and has no wait states. That should introduce some extra stress on the flash subsystem of the microcontroller. All of this is to try to figure out which kind of effect the aging or the degradation has on the different subsystems of the devices. And once we run the experiments, we get this kind of plot, which is a bit too much, so I will explain a bit. In the rows here, up and below, we have the buffered and the unbuffered version of the configuration of the device, and in the column we have the different payloads. On the right axis, we have the maximum error-free frequency, so the one at which the device starts failing. And on the left axis, we have the degradation of this frequency as temperature increases. So, for instance, let's take an example of here, the unbuffered RAM read and write. We can see that when it was 30 degrees, it was around 50 megahertz, and when it reached 80 degrees, it went down almost to 44 megahertz. And this total here is the total degradation, so between the initial and the last part of the samples. And some takeaways that we have from this is that the unbuffered part, so here down, the payloads have heavy memory usage, such as the matrix here, and the RAM read and write, and the flash. They fail at lower frequencies. We can see that because the orange lines are lower than these ones that are actually running from RAM. In the buffered part, we actually see that the multiplication of matrices here is failing at the lowest frequency of all of them, and we assume that it might be due to some no sequential access and all the usage of the arithmetic logic unit. But in general, across all of them, we observe a sort of 2% approximately degradation of the maximum error-free frequency every 10 degrees of temperature that is increased on the microcontroller. So, when we look for the maximum error-free frequency, we also observe that errors don't just appear, they start creeping up. So if we run the payloads 500 times, which is what we do, we actually can calculate how bad we are in the execution of each of the payloads. So let's imagine that we are incrementing the frequency of the clock from 42 to 58. This is how it looks like when we count the amount of errors at different temperature settings for the unbuffered matrix payload. That means that we start with 0 errors and then it starts increasing, not linearly, but proportional to the proportional to the frequency here until it comes up to 100%. Some tests keep working with 100% error. Some they just crash the device. Funny enough, the matrix payload is the only one that just doesn't crash immediately and has this nice transition, which is actually pretty good for this method, because when we are searching for the frequency, doing a bisection across the frequency space, we can actually find that we have parts where we have positive errors, and we have to decrease the frequency without having to reset the device because it just crashed, like it happened on all of the other payloads. So, yeah, in these plots, basically we have the shaded parts are the interquartile range, and the median value are the solid lines, and we can see how all of them, as the temperature increases, they move towards the toward left, which is what we're hoping for to detect aging. So, like I said, matrix is the only one that shows this on both configurations, and the CPU and the RAM March didn't show this behavior at all. So, considering these nice features, we want to kind of compare all of the payloads, and for this we propose to use 3 metrics. One is looking at the maximum error-free frequency, so when it starts failing. We normally would like a frequency that is lower, because that means that we are activating more critical paths. That means that we are making the device fail at lower frequencies. Regarding the execution time, we would like to have tests that are as fast as possible to be able to, well, test as often as possible. And it's also nice to have an error transition. That means that we don't crash the devices each time we are running the test, but we actually can approach the maximum error-free frequency with an idea that we are in the area by just looking at the amount of errors that it has. So here we have, for each of the devices, we give them cookies or code, depending on how good they do. And they seem to do, the matrix actually is pretty good. The CPU was not that great because they didn't have, the RAM March, the CPU didn't have a good error transition, although they were really fast because it was just running from RAM, and also didn't have to fetch any instructions from flash. But the matrix in this case, although it was a bit slower, it showed an error transition on both configurations, and the maximum error-free frequency was the lowest in one configuration and one of the lowest in the other one. So yeah, the matrix against the cookies. Now, we proposed all of these payloads basically from what the vendor provides, from what other people are doing in the literature, but of course in my wish list would be really nice to actually generate these payloads automatically to optimize for all of these metrics that we care about for the automatic test. And given that actually Christmas came a bit early, we have a pick on what we are doing currently to actually make that happen. So automatic self-test generation for aging detection on microcontrollers. I will just go briefly over this. The idea is that we have an initial set of payloads, so firmwares that we generate automatically. We evaluate them on the hardware-in-the-loop setup that we showed before. Here we calculate the maximum error-free frequency at 2 temperatures and calculate all of the other metrics like the execution time, and we observe the error transition. With this collection of payloads, we can actually update a policy that would modify them. We select the next generation of payloads based on how well they did, and we apply mutations regarding, depending on a given policy. And for this policy, what we are testing currently is to use some contextual banding algorithm that would take the firmware, calculate some metrics, based on this, propose a change or mutation operation on the firmware, and update the firmware correspondingly. And with this new firmware, we just inject it again in the loop and do this iteratively until we get a payload that actually does better than the ones that we were testing. And we did some initial tests for this. In this plot here, we can see, that's a bit too clear. We have the execution time, the maximum error-free frequency, and the frequency shift. These are the 3 features that we cared about. In blue points, we see the generated firmware, so the ones that we generated with our automatic procedure. And here in small, we have the baseline firmware, which is this, the vendor CPU test. And we can see that it's down here, although it is pretty fast. The frequency shift was not that great compared to other frequency shifts of 11% that we can achieve with our method. The same goes for the maximum error-free frequency. It is pretty high, and we actually, with this automatic method, managed to come up with firmwares that have much less maximum error-free frequency. This is still ongoing work, but for now it looks promising because we have more than double sensitivity to degradation by generating our firmware automatically based on this iterative method. So now to conclude, well, we saw hardware ages in general. We observed for the SRAM startup patterns. We can use that to detect the usage time of the devices. On the FPGAs, we measured and monitored the slowdown of the propagation delay in long-term operation, and we can forecast that using some machine learning models. We can detect with our technique the degradation of microcontrollers, and we can even be better than just the normal vendor test by doing an automatic generation of that firmware. And in general, machine learning has enabled the detection and forecasting of all of this degradation and supports thus the predictive maintenance in large scale and long time operations such as European XFL or toy production. So in general, aging is observable, measurable, and modelable. And as we like to say in this initiative, test today and deliver presents tomorrow. Yeah. Thank you.
Yeah, thank you very much. Do we have questions? Maybe from remote. We don't see the people from Dresden, but
we can see them.
Here we are.
There are some clapping. Okay. I don't know if they're talking.
Would it help if you have a clear understanding of the source code regarding the prediction of which states are used?
Can you repeat the question, please?
Whether it would help if you have a clear understanding of the source code to predict which memory cells and so on would be used.
Well, I mean, you could, yeah, I mean, probably not of the source code. It will depend on the binary, actually, where the memory will be allocated and where it's going to be used. There is some work towards actually using this to some sort of memory scrubbing to prevent overusage of certain areas. So if you can actually, in your, let's say, linking time, move around where you actually allocate or where you are going to put your variables, you could sort of use your RAM more homogeneously, let's say. Yeah, then of course you would need to have an understanding of the source code, or more like from the binary file perspective, yes. Martin.
About the machine learning stuff. So first of all, I wasn't really clear what, maybe for that you can go to slide 18, what actually the classification is you're using, and so what classes are you using, what's your positive, what's your negative?
Yeah, so the classes that we're using was basically try to put the devices in usage time, so let's take the 1 for example here. So you can say in that part whether the device X has been used for 1 or 2 or 3 or 4 months or whatever until 18, and then when you increase this, when you change the usage resolution, basically you say, okay, now my box is like, or my classification label is 2 months long, and so on until it gets 9, where it's a binary classification. We also did a regression for this, of course, that's also on the paper. Yeah, so we tried both approaches.
I understood this plot, but I was thinking, I thought that you were trying to predict some errors there, but I think that you are doing later. You're basically just trying to predict how long the device was in use.
Yes.
Okay, yeah, okay. Then makes sense. But going to the forecasting, slide 32. 32. You have this training window is moving, right?
Yes, so there are two cases, basically one where you have a fixed length and one where you don't have one. Let's say that you have a fixed length, then you forecast first one value at the edge of the forecast horizon, then you move the window once to the right and you do the same, and they just keep repeating.
Yeah, then my question would be if you saw any model degradation and how you countered it if you saw it.
Model degradation.
Yeah, that the model, the trained model itself degrades because you're adding more training data.
No, but that's, yeah. So this is this plot. Here, in all of the ones that have an L with a value, the window is fixed. So there's no more training data, right? So,
okay. So you're retraining your model every time.
Yes.
Not adding to
but the green one is actually with all of the data. So there, the training part gets bigger and bigger, and yeah, that is actually similar to the other one. So there doesn't seem to be affecting that much.
Okay. Thank you.
I have another question.
Yes.
Okay. Could you comment on how invasive these methods are? So, like, I think for the SRAM, I could imagine you can just on startup have a small program that somehow checks the SRAM. For the FPGA, I'm not sure. Is like you will probably have to have this oscillator ring permanently running, like.
Yeah, I mean we did both.
Active.
Yeah. I mean it takes space, right? In this case. In the SRAM you can do it on startup, that's no problem. The ring oscillator you can actually have with the application. That's what we did during deployment of the 280 days of operation of the XFL, and we actually deployed on the machine while the FPGAs were running and doing their normal operation. And even with the measurement procedure, it didn't really disturb anything. We were just taking the measurements from the PCI Express interfaces that they exposed, and it didn't really affect the operation. I mean, we did measurements every 2 hours. It probably could have been more, yeah, but everything was working correctly. And then for the microcontroller one, sorry, yeah?
Yeah, I think you just wanted to answer the question.
Yeah, so the microcontroller one, that definitely can't happen. So it's an online self-test in that you don't need external devices, and you can run it when it's deployed. But that you can't do while it's in operation. So the idea is that you would take some maintenance time, but also it doesn't have to be every 2 hours, right? I mean, the microcontroller measurements you can do every month or however you think it makes sense, because it wouldn't be too much if to do it too often. But in that case, yeah, you can't run your application payload while you're running the test.
Thank you.
So, maybe questions from here. Nobody?
Too many.
So I'd be interested in how does the what would you say on the execution time of the test payloads?
The microcontroller ones, or?
For example, yeah, the microcontroller. How much would you realistically need to extend those in realistic deployment to find errors that happen very rarely? Because usually, I mean, the microcontroller isn't really considered safe if it only triggers an error, whatever, once an hour or once a day. That would be still pretty bad, right?
Mm-hmm.
So what can you do to basically make sure that it triggers fast enough to still be a valuable runtime self-test?
Yeah, I mean, I'm not sure I understand, because I mean, what you're doing here is you're increasing your own frequency to actually trigger the error, right? Mm-hmm. And during that time, you can't run your application. But normally, you're overclocking the device in such a way that it's off spec, at least where it's new-ish. And in that case, what you're looking at is basically tracking this maximum error-free frequency, maybe even getting some information on how much overclocking you can do for your application if it's like CPU bound or something like that. But I don't think you would need to run this test every day at all. I mean, I don't think it would pay off. It doesn't make sense.
I was more thinking in the direction of how long you need to run it to find errors that are not so easy to trigger. I mean, with the overclocking, of course, it just gets more sensitive, so to say, to problems. But does this automatically also imply that
I wouldn't think you would find errors without the overclocking, unless the device is too degraded.
Okay.
I mean, yeah. I mean, it's hard to trigger it, right? It's also the idea of this was that this is tested as a sort of black box, so it's hard to actually understand exactly which is the trigger of the failure. You can only get some ideas from the subsystem, so it's pretty fuzzy.
I mean, you could basically twist the question a little bit around and say, like, if you run the system at a high frequency and then it induces an error, does it guarantee that there is no error on the within spec operation, basically?
Probably not. I don't think so. I mean, maybe there's
hard to say without a huge amount of empirical data.
I mean, you would need a lot of data and a lot of time testing probably, and I don't think that's really feasible unless you have a lot of time and money to spend. But that's why we do the accelerated testing, right? That's, but yeah, no, I mean, you could calculate kind of like the probability. Okay, given that we fail so much in 60 degrees, then how it would look like in 20 or 30. Yeah, but I mean, this one not at all. Yeah.
Thanks for the talk, first of all. So I understand that you presented framework you guys were working on, but I was wondering, like, so when I'm at home looking at my electronics tinkering desk, I have this kit of transistors, for example, with different kinds of NPN, PNP, whatever transistors, and even with the PNP or NPN transistors, there are like 20 different kinds that have different threshold voltages, turn-on times, and whatever. And so looking at it from the electrotechnical, from the electrical engineering perspective, if you look at different kinds of transistors and how they age compared to each other, like are there different memory sets, like maybe depending on whether they've been manufactured with like 10 nanometers or 20 nanometer architecture and whatever, and how that also the electrical engineering side affects the aging part.
Yeah, no, we didn't look into that, but there's people that did look into that. There's a lot of reliability engineering tests that are done whenever there's a new node technology going on, and they say, okay, yeah, I mean, there are papers testing since 180 nanometers until today, testing all of the nice FinFETs and 3D structures, and how the MBTI, so the same exact aging mechanisms affect that kind of thing. Yeah, it changes. So, for instance, in this sort of 3D FinFET structures, you have effects of self-heating because of the 3D structure in the silicon that they have. They actually are not that well dissipating the heat, and that means that things like MBTI actually get much more extreme. Also because we are shrinking the footprint of each of the transistors, but not shrinking the voltage that we apply them in the same rate. The electric field that is applied is much bigger in comparison, so that also induces more diffusion. That is the main cause for MBTI. So yes, there's a huge difference, but we were focusing mostly on the devices that we have at hand normally, so microcontrollers that don't come in these technologies at least yet, and the FPGAs that we had deployed. But yes, I mean, the same effects normally apply. You would probably, I mean, you can run the same test probably, but if you talk about the models, you would more likely need to retrain that with the new data. But I would say the main conclusions actually here apply for the new devices as well. They might be more resilient or less resilient, but the principles of failure and test should be similar as well. Yeah.
That brings me to a follow-up question from Jan. Do you see any quantity, integrated or relative, absolute, I don't know, that has low dependency on the individual hardware type? So that you could, do you see some hope of some general measure that says, okay, if you detect something above that threshold or above that kind, that would actually be valid for many devices, device types, I mean. Not,
I think I understand. And I think if you actually look with microscope a bit, or more like actually from far away, this is what we did. I mean, if you remember the beginning of the talk, I talked about threshold voltage, and that's actually have been the constant across all of the things, because in the SRAM we observe the threshold voltage by looking at the startup patterns. In the FPGAs we actually see a change in the threshold voltage which affects the propagation delay of the transistors, and in the microcontroller the same happens. So propagation delay changed by threshold voltage, for instance. So yes, I mean that's a known indicator also if you're looking at a specific transistor like normally you do. That's a good indicator, but depends on the device how you can actually get to measure that, right? I mean, in SRAM, well, you need to do all these tricks with a startup to actually look at the thing, because we can't put the scope and measure the particular nodes, right? And so that's why the approaches are different, but I think if you think about it, they try to measure this, not the same thing, but the similar effect, kind of, in different ways. So yeah, I would say that's a good central point, I think. Yeah.
Was there a question?
Yeah. Regarding this SRAM, I mean, with the bias of 1, 0.
Yeah.
I mean, what I understand from there, of course, if you have the battery, I mean, on a flash, at some, or basically when you load stuff on the SRAM, so you will probably have more zeros. And as understood, this would basically shift that towards to 1. But what happened in other regions, for instance, where you have a more homogeneous distribution of...
Yeah, then it doesn't change. I mean, that's probably what we saw here. Let me move the people. So this is the SRAM of the Admel microcontroller that has been running a single firmware, and the limit, which is kind of here, is the firmware usage, and you can see that this part, which normally if you just flash a normal ELF file to the thing, is not initialized at all, and then this part was not used. So that part actually is more homogeneous than the other one that has more stable bits. That means that all this part is just changing because it's still random and not biased against the other one that was more, let's say, hammered with the same firmware all the time. Yeah. And the lower part here, actually, they were using for the bootloader, so that's if you were wondering. Yeah.
So a little bit related to that, is there empirical data or something that suggests that this, what you can clearly observe that it like has an effect and you see that it ages based on the usage, but that specifically for the SRAM that it actually induces an error later on, like how bad does it get before it actually breaks? Or
yeah. I mean, I think it is particularly in areas with, like I say, high radiation, like these devices were running inside the accelerator tunnel. There's studies that actually show that this 6 transistor cell, when the threshold voltage is just too high, then in that point, just a slight hit of a big particle, let's say, would just flip the bit. So that happens, that has been studied, and that's a fact. It also happens in the other direction also. If the threshold voltage is too low, then it might happen that the transistor is actually latched up. That also happens in the other direction due to radiation. That happens in space. For instance, that's common in these kind of devices. Yeah, well, that's why many of the FPGAs are sent out to high radiation areas. They just do some scrubbing to reconfigure the device, so the SRAM of the device periodically to avoid these kind of errors. Yeah.
more questions? Neither here nor there?
No, doesn't seem like that. No.
No. Yeah, I guess then we thank Leandro again.